AC circuit, please take down. AC means alternating current. It is a type of current that flows in one direction. It is a type of current that flows in one direction and then in the reverse direction. Reverse. And then in the reverse direction. It was discovered by Nikola Tesla. So, Nikola Tesla in 1882. It was discovered by Nikola Tesla in 1882. One line space paragraph. Take down. A circuit is the path provided for the flow of electric current. A circuit is the path provided for the flow of electric current. So first of this, a circuit is the path provided for the flow of electric current. Hence, an AC circuit is the path provided for the flow of AC means alternating current. Fine. So hence, an AC circuit is the path provided for the flow of alternating current. That's AC. Full stop. There is AC, there is DC. So what's different? Paragraph. One major difference between an AC circuit and a DC circuit is that. So let's see what differentiates an AC from a DC in terms of components. What differentiates an AC from a DC in terms of components? One major difference between an AC circuit and a DC circuit is that AC circuits contain three major components. Three major components are resistors, capacitors, inductors. So AC contains these three. While DC circuit contains resistors, capacitors, and battery. Right. And battery. Take that, please. Take that. Let's define. Let's highlight few of them. The resistor opposes the flow of current in the circuit. The resistor opposes the flow of current in the circuit. The capacitor is used to store charges. Resistor opposes the flow of current in the circuit. Capacitor is used to store charges, while inductors are used to store electrical energy. While inductors are used to store electrical energy in form of magnetic energy. Inductors store electrical energy in form of magnetic energy and control signals in the AC circuit. And control signals in the AC circuit. Take down please. Take down. Given the maximum RMS value of an AC, take down. Given the maximum current, given the maximum in bracket peak current, that is I naught. Given the maximum or peak current in bracket I naught, okay, do this way. Given the maximum, that's peak current and voltage. Current and voltage is add there, and voltage, that is to 6 times I naught and V naught respectively. Given the maximum, that's peak current and voltage respectively, that's I naught and V naught respectively, then the RMS value, of the current and voltage are given by RMS equal to I naught all over root 2. And VRMS equal to V naught all over root 2. Alright. Please, RMS equal to peak all over root 2. From here, look at this, from here, I have that RMS is equal to, this gives you, look at this, this one here, in mathematical form, is the same as 1 all over root 2 dot I naught. They are the same thing. Please punch 1 over root 2. What do you have there? 0.70771. Alright, I naught. So RMS is equal to 0.7071 I naught, and in the same way, what is this? VRMS by logical extension, VRMS is equal to 0.7071 V naught. Please think of this. That the peak is equal to 1 over root. The RMS is equal to 1 over root of the peak value. So I have these two things. Recall that from Ohm's law, V is equal to IR. Recall that from Ohm's law, V is equal to IR. If I write this in terms of RMS and peak, you have that V RMS is equal to I becomes I RMS times R. Please think of this thing. That VRMS is equal to I RMS times R. This from Ohm's law. Also, this is in terms of RMS. In terms of peak value, we have that V naught peak voltage is equal to I maximum or peak current and then R. So note that we can write what we call Ohm's law in terms of RMS or in terms of peak. The same thing, just change it to RMS and then peak, that's all. Sample problem. Sample problem is an AC voltage whose peak value is 120 volts is across a 40 ohm resistor. What are the values of RMS and peak current in the resistor. Look at it. Solution. Please check. What's the first you have there? Peak value. You have peak value. Peak value of what? Voltage. So number one, they said, look, it said an AC voltage, the voltage. So I have V naught there, AC voltage, whose peak value? So that's this one here, It said peak or maximum voltage. So I'm giving V naught, number one, the peak voltage, V naught, as being equal to 120 volts. Next they said, number two, across a resistor R of how many there? 40 ohms. You have to find the RMS value and peak current in the resistor. Please, 40 ohms. I said 4 ohms?
Yes.
Okay, no problem. Okay, 4 ohms. Alright, you have to find RMS and peak value of current in the circuit. Easy. Start with this one, yeah? Start with this. So let's get peak current first. Recall that. Let's get peak current. Recall that we said peak voltage using Ohm's law is equal to peak current times the resistance. To get peak current, divide here by resistance, divide here by resistance. That means peak current I naught is equal to peak voltage V naught all over resistance. That's equal to V naught is 120 all over, this one is 4. So what do you get there? 30 what? Amperes. Current in amperes. So I've gotten the maximum current. If I've gotten maximum current from here, recall also that if I'm to get RMS value, we said RMS is equal to I naught all over root 2. That's equal to I naught is 30 all over root 2. Please punch for me. What do you get? Sorry? 21.2. 2 direct. Give it to the P. 2 1 what? 2 1 amperes. Alright. 21.21 amperes. So that's it. Any question, please? That's it. Any question? Next up is mean/average value of AC. The mean/average value of current and voltage. That is current IAV. This means average value of current, and VAV, average value of average value of current, and then average value of voltage is 0.637 times their respective peak value is 0.637 times their respective peak value. That is, average current is equal to 0.637 I naught maximum current, and VAV average voltage is equal to 0.637 V naught. So for both of them is 0.637 times the peak value. Please note this one here. Form factors. This is the ratio of the RMS value to the average value. This is the ratio of the RMS value to the average value. Whether for current or voltage, form factor is a constant, it's the same value. We said form factor K is equal to RMS value all over average value. Let's say I'm considering what's it called? Current. So this becomes, let's say I'm considering current. This becomes IRMS all over IAV. So I have K equal to this over this. If you check, I expressed this one earlier in terms of maximum. We said in terms of maximum, IRMS is equal to 0.7071 I naught all over. In terms of average, we said IA is equal to 0.637 I naught. Alright, from here, this cancel this. Please punch this. What's K? Punch these two values. What's K? 1.11. Please be noting these values because we use them in our solving. I just want to get chunks of some concept that we use. So 1.11. Don't forget it's RMS all over P. Alright. Look at this. We'll do an analysis. I'll do part of it and you continue the other part. Right? So just observe what I'll do now. Follow the reading. I'll stop halfway and you complete for me, please. Look at this, please. Let's analyze an AC circuit. Let's analyze an AC circuit. Let's analyze it. Alright, so we said AC circuit is different from DC because for AC I have three major components there. Number one, the resistor. Number two, I have capacitor. Number three, I have inductor. This one for opposing the flow of charges, or can say measuring the resistance of the circuit. This one here for storing charges, capacitor. This one here for storing electrical energy. Now, here's what we'll do. We'll consider AC circuit that has only resistor. We'll look at how to draw the diagram and how to make analysis from it. When we are done, look at the next one. We'll look at AC circuit that has only capacitors. We'll make some inferences, derive some formula. We'll look at AC circuit having just inductors only. We'll get the diagram, draw some diagrams, get some formulas. When we are done with this one individually, we'll take them in twos. We'll look at AC circuit having resistor and capacitor. We look at AC circuit having just resistor and inductor. All of them have a different formulas. Then finally look at AC circuit having resistor, capacitors, and inductors combined. All of them have their separate formulas. Look at them together. So let's start with look at it. Let's start with AC circuit having resistor only. Think that please. Stop anyways. AC circuit having just resistors. Alright, so let's look at AC circuit containing, for the first one, let's look at resistor only. First things first, the circuit symbol for a resistor is this. Circuit symbol for a resistor is this. That is either this one here, this, or this one here, this. Alright, so any of these two is the electrical circuit symbol for a resistor. There's one called variable resistor, also called a rheostat. What they call a rheostat? What a rheostat is simply a variable resistor. What does it mean? It's a resistor whose value can be altered. That's it. Usually if I have a resistor, if this resistor is let's say this is 3 ohms. for instance, it will always be 3 ohms. It doesn't change. It's fixed. Why? If I'm using a variable resistor, rheostat, by the way, your rheostat symbol is this. The same thing, just that because I have an arm like this, it becomes a rheostat. Same thing as this one here. Same thing with this. But I have this. Install a rheostat. That's it. Alright. It's a resistor whose resistance value can be altered or changed. That's it. For this one here, when we say containing resistor only, your circuit is this. Look at it. Now, look at the way I'm sketching this one here. You sketch the other ones. With this is how you draw your AC circuit with resistor only. So here's how you do this. Depending on if you want to pick this or this. For this case, I'm choosing this one here. So it becomes this one here. Then you have from here, this is VR. VR means voltage across the resistor comes down this way, having this. You have this. You have VN. Right, then you have this one here. This one shows the current I. Alright. When I give you the question in the exam, they'll give you in theoretical form. It's now left for you if you want to draw the circuit or not. But our advice, if you're fast enough, draw circuit. It gives you more marks. Right, draw circuit. So this is how the circuit looks like. Does this? You can see this contains in this circuit. I have only resistor here. VF represents voltage frequency. Please don't forget. VF here represents voltage. F is frequency. VR is the voltage across the resistor. This one here is the resistor. I here is the current in the circuit. Please, that's it. Right. V voltage. F frequency. I current to the circuit. VR voltage across resistor. So in the question, they'll give you voltage and still ask to find voltage across resistor. They are two different things. R is resistor. Alright. Let's get our first formula, please. Let's get our first formula, please. For this one, the formula is this. From Ohm's law, we have that V is equal to IR. Let's take maximum. We say V naught or V maximum is equal to I naught times R. This is the only formula per se for AC continuous resistor. Just this one here, that's all. Number 2, let's see AC circuit continuing. Number 2, inductor only. Inductor only. Take that please. Take that please. Inductor is represented by F. Please, resistor is R, as you can see here, measured in ohms. Resistor used to measure resistance in ohms. Inductor is used to measure inductance in Henry. Please, inductor is used to measure inductance. And the unit is Henry. You know what is Henry, I mean? Take that please. The circuit symbol for inductor, the circuit symbol for an inductor is this. The circuit symbol for an inductor is this. This is like an inductor symbol, L. Next up please. Let's sketch an AC circuit that has inductor only. How do you sketch it? This same thing comes here. So I'm drawing exactly the same thing, just that I'm replacing this by this. So hence, my circuit symbol for an AC circuit having inductor only becomes this. Becomes this this the voltage becomes no longer VR but what? VL. Voltage across the inductor. Yes, L, inductor, this, right. And then, so it comes down, this one, yeah? This is your voltage frequency supply. Of course, one last thing, your current flowing this way. So you have I. So this is basically your diagram. Observe the same thing. I just changed the R to L. I changed circuit symbol, and I changed VR to VL. That's all. So this is AC circuit containing inductor only. Take that please. Are we done? The opposition to the flow of current in an inductor circuit is called reactance. Reactance given by XL. What we said mathematically, XL is equal to 2 pi L. N is what? Frequency in hertz. L is inductance in Henry. Note, there is a correlation between frequency and angular frequency. Note that angular frequency ohms, it's called omega. Note that angular frequency omega is equal to 2 pi the normal frequency. Angular frequency is equal to 2 pi f normal frequency. In other words, we can say that the reactance across the inductor circuit, that's XL, is equal to 2 pi f is omega. That becomes what there? Omega f. Alright. Omega f. That's equal to omega f. While the voltage across the inductor circuit, V is equal to IXL. Worthy of note are these three formulas. That the voltage across the inductor circuit VL is equal to IXL. Note this one here. Number two, that the reactance, which is the opposition to the flow of current in an inductor circuit, is XL, which is equal to 2 pi FL. Number three, that the reactance can be expressed in terms of angular frequency as XL equal to omega F. These three things. So for this one here, you have these three. So I have this. Alright. Let's look at the third part. Let's look at AC circuit containing capacitor only. We said a capacitor is a device for storing electrical charges. Your circuit symbol for capacitor is this one here. So I have this. The unit for capacitance is the farad. That's farad. That's F. That's the unit for capacitance. For this one here, your circuit is this. So let's look at AC circuit having capacitor only. So this, please, while drawing this, make sure that these two have equal lengths. VC, this is C. You have this point here. So here becomes your voltage frequency supply. You have this. You have this. So you have this here. This one here is R, the current. So you have this. So what we want about this? Take down. Take down this. The reactance, take down. The reactance, which is the opposition to the flow of current in an AC circuit containing capacitor only, in an AC circuit containing capacitor only, is given by XC. So XC means reactance. Some authors call it reactant. Some authors call it reactant. Whether they call it reactant or reactance, it means the opposition to the flow of current. So for capacitor circuits now XC is given by the formula XC equal to 1 all over 2 pi FC. Please take note. Take note, please. For XL, there is no inverse. XL is 2 pi FL. For C, there's an inverse. It becomes 1 all over 2 pi FC. We already said that 2 pi F is equal to angular frequency. So hence, the reactance in the capacitor circuit XC is equal to 1 all over, all of this, 1, 2, 3, is angular frequency times C. So you have it. Hence, the voltage flowing through the capacitor circuit. Hence, the voltage flowing through the capacitor circuit is given by Vc equal to Ixc. Alright, so these are your notes here. Note this formula here. Voltage across the capacitor. Note this formula here. Reactance across the capacitor circuit in terms of normal frequency and in terms of angular frequency. At this point, ladies and gentlemen, we are done considering them in ones. Let's now take them in twos. If you ask me, I feel it's easy. Everything here deals with Ohm's law. Ohm's law basically is this: V is equal to IR. Voltage equal to current times resistance. Now hang on. If it is a resistance only circuit, V is equal to IR, no problem. If it's an inductor circuit, V is also equal to IR, yes. But the difference is now this: for inductor only circuit, you cannot be having resistance. It's not okay. So what do we do here now? We substitute this one here with something else, which we call reactance. So for inductor only, the same format, V equals to I, and then resistance in terms of inductor, which we call reactance. If you look at definition for resistance is the opposition to the what? Flow of current in a circuit. If you look at how we define reactance, said reactance is simply the opposition to the flow of current in what there? An inductor circuit. So if you look at it critically, both of them are still what there? Resistance. So this one here is resistance in terms of an inductor. That's it. I will say this is equal to what there? 2 pi FL. That's all. The same idea works with capacitor. That V is equal to I, no longer R or what there? Xc. Same concept. X is what there? 1 over 2 pi Fc. And that's it. Look at this. Everything is just Ohm's law. Just express them correctly. That's all. Alright. Next case, please. So we've just considered AC circuit containing just one element. resistor, inductor, capacitor. Let's take them in twos. So this is number 3. Number 4, AC circuit containing resistor and inductor only to combine. Alright, so let's now take them in twos. In twos, you're taking, first we're taking resistor, inductor. Listen, it's resistor, inductor in series. So it becomes RL series circuit. Resistor, inductor in series. So here's the diagram. For this one here, I have this one first. I have resistor first. So this one here, resistor first, connected to an inductor. So perhaps inductor next. I have this. For this one, you have to show the voltage across the resistor. This is resistor. For this one here, you have to show the voltage across the inductor. That's Vn. Call this L. Bring this down, showing your voltage, showing the voltage frequency supply. Then you have this. Alright. So this is RL. Okay, one last thing, current. What else is this current? So we have this. Alright, so look up. As usual, from Ohm's law we said V is equal to IR. We know this. That means the voltage through this circuit is equal to I, normal current. But we know that we can't use R in this case. So hence, the arrow in terms of this, that's the resistance, in terms of RL, what's it called? Take that please. The opposition to the flow of current, in an RL series circuit, the opposition to the flow of current in an RL series circuit is called the impedance of the circuit. The opposition to the flow of current in an RL series circuit is called the impedance of the circuit. That's Z. Impedance now is Z. For this is RL, so it becomes ZRL. So it's ZRL. It's called impedance. So in this case now, impedance replaces this. What's impedance? It's simply your position to the flow of current in an RL series circuit. That's it. So for this one here, what's the formula? Note that ZRL is equal to the square root of this one square, R squared plus this one square, XL squared. This is resistance in terms of resistor circuit. We've discussed this. This is resistance in terms of what? Inductor circuit. So just take the square root of each of them square. That's right there. Alright. So the impedance in an RL series circuit is equal to the square root of R squared plus XL squared. That's it. Such that the voltage flowing through the circuit, V, that's V of RL, is equal to current times impedance, ZRL. Current times impedance, ZRL. Sample problem. Number 5, let's look at AC circuit containing resistance or resistor and capacitor. So RC, resistor capacitor series circuit. Series circuit. RC. So the same idea here. Draw your diagram. For my diagram, I have this arrow. Permit me to use this one here now. Still the same thing. We said either this one or this one here. It's still resistor. You ask medical student what is this? They tell you that it's heartbeat, right? It's not heartbeat though. It's resistor. So let me change the body. The body heartbeat. This stuff. This is my resistor. This becomes VR. This is my capacitor. This becomes VC. This is voltage frequency supply. This is current I. Alright, so this is my resistor capacitor in series. That's it, series end to end. Series end to end. For this case, the opposition to the flow of current in my RC series circuit is still called impedance. So it's still impedance. So impedance here is called ZRC, where ZRC is equal to square root of R squared plus XC squared. Alright, so we have this. And the voltage flowing through this circuit is given by VRC equal to I ZRC. We have this. What's the unit for impedance? What's the unit for impedance? Huh? Ohms. Ohms. When we did resistor only, V is equal to IR. Inductor only, V is equal to IXL. Capacitor only, V is equal to IXC. Resistor inductor, V is equal to IZRL. Resistor inductor series. Resistor capacitor series, V is equal to IZRC. So everything is just the same idea. The difference now is just this stage, what it represents, that's all. Right? This one, 2 pi FL, 1 over 2 pi FC, square root of R squared plus XL squared, square root of R squared plus XC squared. That's all, no big deal, no big deal. That's all. The question is this, resistance here is measured in ohms. What about this one here? Huh? It's still ohms. It's still ohms. Alright? All of them, that's this, are still they are still as resistance, but in different sets. So everything here, 1, 2, 3, 4, 5 is in ohms. One final task. Let's look at 3 of them combined. Alright, so one last one. Let's look at all 3 combined. RLC. So resistor, inductor, capacitor circuit. This is where I have this. Each of them have the voltages across them. Take that please. The opposition to the flow of current in an RLC series circuit is called the impedance of the circuit ZRLC. It's called the impedance of the circuit ZRLC, which is equal to the square root of R squared plus XL minus XC squared. So picture this one very well and see how your formula works. XL XC squared. Wow, this. Correct. The voltage across the resistor is given by VRLC, which is equal to I times ZRLC. I times ZRLC. That's it. Look at two more things. Just solve past question confidently. Look at two more things. Solve past questions confidently. Let's look at voltage multiplication. Voltage multiplication is also called the Q factor. Voltage multiplication is also called Q factor. It is the ratio of VL to applied voltage. It is the ratio of VL to applied voltage. That's equal to VL all over V. We said VL is equal to IXL all over V is equal to IR. So over from here, I can cancel I. So the Q factor, Q, is equal to XL all over R. The ratio of the reactance of the inductor to the resistor is called the Q factor. It's called the Q factor. What's XL? What's the formula for XL? 2 pi FL all over R. So we have this. One last thing, please. One last thing, please. One last thing, please. Let's look at resonance frequency, please. This is the frequency, resonance frequency. Resonance frequency, please. This is the frequency at which resonance occurs. This is the frequency at which resonance occurs. At resonance frequency, the reactance in the inductor circuit is equal to the reactance in the capacitor circuit. At resonance frequency, the reactance in the inductor circuit is equal to the reactance in the capacitor circuit. So what is this? That is reactance XL in inductor circuit is equal to reactance XC in capacitor circuit. We've got this one here as what there? 2 pi FL, or before then, express this in terms of angular frequency. We have that omega L is equal to 1 all over omega C. So we have this. Make omega subject of the formula. Your instep is this. This one comes this way, L goes this way. So I'll now have omega multiplying, so comes here, omega is being equal to 1 all over L, take this position, I have LC. From here, what I have here, is omega times omega. That gives you omega squared is equal to 1 all over LC. Okay. But I know that omega angular frequency is equal to 2 pi f. In this case, look at it. In this case, since I'm considering the idea of resonance frequency, and since I'm equating reactance of inductor to reactance of capacitor, what I have here is not just 2 pi f, but what there? 2 pi f r. I'm changing here to r because I'm considering resonance frequency. So hence, in this case, I'll now have that omega squared becomes 2 pi f r squared. Omega squared is equal to 1 all over LC. My case here will be to take square root of both sides. If I take square root of this and then square root of this, what happens here is that square root cancels square. So I'm having 2 pi f r is equal to the square root of it. I can separate these two with the idea of what's called indices. I can separate these two or sorts. If I have these two here, I can rewrite this as saying square root of 1 all over square root of LC. And that's equal to square root of 1 is 1 all over root LC. What next? From mathematical approach, these two can come down here. Or you can say divide both sides by 2 pi if you want to. Or simply, these two comes down here. So it means that resonance frequency Fr is equal to 1 all over 2 pi square root of LC. This is your formula for resonance frequency. That Fr is equal to 1 all over 2 pi root LC. Please note this, please. Take that, please. And let's note these few things and then we can do something else. Let's note these few things. We can do something else, please. Take that, please. Let's look at phase angle. Let's look at phase angle. Look at phase angle. For resistor inductor series circuit, the phase angle given by theta is equal to tan inverse of XL all over R. For resistor capacitor series circuit, the the phase angle theta is given by tan inverse of XC over R, and 1 last over 3. Finally, for RLC series circuit, the phase angle theta is equal to tan inverse of XL minus XC all over R. Alright, so please note these three phase angle. Let's do question, please.